J'ai jamais dit non. J'ai juste laissé le temps courir, partir, venir, mourir, courir, partir.
Whoa, this tea is really strong. How much caffeine they put in here? But have you guys ever wondered how they actually measure the amount of caffeine in our beverages? So today in this video, we will explain how chromatography analysis works and how it's applied to determine the amount of caffeine in the tea using theory, methodology, and also real calculation examples. Tea is one of the most used caffeinated beverages in the world. The caffeine that found in tea is bitter, white, crystalline metacetine, and a member of a class compound known as alkaloids. Alkaloids are basic nitrogen-containing compounds present in plants. So today, objective of the experiment is to separate caffeine from the tea using the thin layer chromatography plate. Then, what is the thin layer chromatography plate? Thin layer chromatography plate, in short, TLC plate, is a stiff sheet of glass, aluminium, or plastic that coated with a micro-thin, chalky layer of polar powder, which is usually the silica gel. It functions as the track for the TLC, where you place a drop of your chemical mixture at the bottom and let the liquid solvent climb up it. Since most chemicals are colorless, this plate usually contains a fluorescent dye that glows under the UV light. It allows you to see the separated chemical spot as dark shadows against the glowing backgrounds. Lastly, what is a chromatography? Chromatography is a technique for separating and identifying components of a mixture. It relies on two things, which is the first one is the mobile phase and the second one is the stationary phase. Stationary phase is something that stays still like a piece of paper or a gel column, while mobile phase is something that moves like a liquid solvent or a gas. As the mixture travels along, its different parts move at different speed. This is because some prefer to stick with the stationary phase while others prefer to move with the mobile phase. By the end, they are fully separated. So, let's break down how this chromatography technique is used in this experiment.
Okay, now let's move on to the theory. So, thin layer chromatography, or we call TLC, is an analytical technique we use to separate and identify compounds in the mixture based on their polarity. So, in this experiment, TLC was used to confirm the presence of caffeine in the tea extract. This was done by comparing the movement of the tea extract with the caffeine standard on TLC plate. When the TLC plate is placed in the developing chamber containing a solvent, the solvent moves upward through capillary action. As it moves, it carries the compound along the plate. Compound with the lower polarity travel further because they interact less strong with the silica gel. On the other hand, more polar compounds are more strongly attracted to the silica gel, causing them to move more slowly and travel shorter distance. And to measure how far the compound moves, we use RF, or retention factor, which is calculated by dividing the distance traveled by the compound by the distance traveled by the solvent front. If the RF value of the tea extract is similar to the RF value of the caffeine standard, it indicates that caffeine is present in the tea extract.
In this experiment, the apparatus that we need is a TLC plate, 150 ml beaker, a watch glass, capillary tubes, 10 ml graduated cylinder, pencil and ruler, UV lamp, and paper towel. And for the chemical that we use is acetone and also hexane. The first step for the procedure of this experiment is preparation of samples and mobile phase. A small amount of acetone was added to the non-caffeine standard vial. The vial was swirled to dissolve the caffeine in the liquid phase. A 1:2 of acetone to hexane was prepared. Using a 10 ml graduated cylinder, 2 ml of acetone and 4 ml of hexane were measured. Combined in the 150 ml beaker and swirled gently to mix. The next step for our procedure is preparation of the TLC plate. The liquid level in the beaker was estimated to be approximately 5 mm. Next, we need to mark the plate. Using a pencil and ruler, a straight horizontal line was drawn across the TLC plate, roughly 6 to 7 mm from the bottom edge. Next, a clean capillary tube was dipped into the extracted caffeine sample and spotted onto the pencil line on the left side of the plate. The tube was touched to the same spot multiple times to concentrate the sample. This spot was then labeled E for extraction. Next, a second clean capillary tube was dipped into the prepared Caffien standard. The standard was potted onto the right side of the pencil line and then labeled C for Caffien. Lastly, the plate was wafted into the air until the spotting solvent completely evaporated. The next step for the procedure is developing the chromatogram illusion. The TLC was carefully lowered into the beaker as evenly as possible, ensuring the origin line set above the solvent level. The top of the plate was rested against the beaker wall, and the chamber was covered with a watch glass. Next, the solvent front was allowed to migrate via capillary action until it traveled between 1.5 to 2 1/3 of the way up to the plate. Next, the plate was removed, placed on a paper towel, and the final position of the solvent front was immediately marked with a pencil. The remaining mobile phase on the plate was allowed to evaporate completely.
Next is the example of result. So, this table summarizes our experiment data and the percent yield of caffeine in tea. In this experiment, we started with a mass of tea bag, which is 2.82 gram, and during the extraction of caffeine in tea, we successfully isolated 0.06 gram of actual caffeine, and this brings the final calculated percentage of caffeine in our tea to be 2.13%. Now, let's break down the step-by-step of the calculation. First, to calculate the weight of isolated caffeine sample, we have to minus the weight of vial with caffeine extracted with the weight of empty vial, and we managed to get 0.060 gram, which is the actual weight of caffeine. Next, to calculate the percentage of caffeine in tea, we have to divide the actual weight of caffeine and the actual weight of tea bag and times with 100, which is 0.06 gram divide with 2.82 gram and times with 100, and we managed to get 2.13%, which is the percent caffeine in tea. Showing this step clearly demonstrate the direct quantitative link between our raw laboratory measurements and our final analytical finding. Once we successfully isolated our crude crystal, the final step was to identify their identity. To do this, we used thin layer chromatography by comparing our extracted sample with a pure caffeine standard. As shown in the table, the solvent front traveled a total distance of 59.0 mm, while both spots migrate exactly at 25 mm up to the TLC plate. To turn this measurement into a standardized value, we have to calculate the retention factor or RF value by dividing the spot distance by the solvent distance. And from the calculated data, it shows that both of the standard caffeine and extracted caffeine has the same identical RF value, which is 0.424. And in chromatography, if the value of RF is identical, it means that the compound share the exact same chemical properties. This perfect match provides definitive, concrete evidence that the crystal was successfully isolated from the tea leaf is indeed pure caffeine.
And there you have it. From the comforting cup of tea you enjoy in the morning to the energy drink and pharmaceutical that power in our modern world. Caffeine is everywhere. Through the power of extraction and thin layer chromatography, we aren't just looking at the spot on plate, we are witnessing analytical chemistry in action. TLC play a crucial role in the chemical and pharmaceutical industry, allowing scientists to quickly monitor purity, identify compound, and ensure that what goes into our body is precisely analyzed. So, the next time you enjoy your favorite tea, you will know exactly what's happening behind the scenes.